Dear children, साडा अज दा टॉपिक है the combined gas law or the ideal gas equation and Dalton's law of partial pressure. पर अपना टॉपिक शुरू करन तो पहला आओ तुहाडे नाल अज दे लर्निंग ऑब्जेक्टिव्स शेयर कर लईए.
Upon completion of this topic, the learner will be able to define combined gas law or ideal gas equation. Define Dalton's law of partial pressure. Solve numericals related to ideal gas equation and Dalton's law of partial pressure. Children, let us discuss gas laws with this animation. This container has volume V containing n moles of gas. These n moles of gas exert pressure P at constant temperature T. When we decrease the volume of the gas, keeping amount of gas n moles and temperature T constant, the frequency of collisions with the walls of the container increases, and thus the pressure increases. This is Boyle's law. It states at constant temperature, volume of a fixed amount, that is number of moles of gas, is inversely proportional to pressure applied. This can be represented as shown on the screen. Students, when we increase the temperature of n moles of gas, keeping pressure P constant, the volume of the gas increases. It means at constant pressure, volume of a given mass of gas is directly proportional to absolute temperature. This is Charles' law. Students, when we increase n number of moles, that is amount of the gas, keeping temperature and pressure of a gas constant, the volume of the gas increases. So, volume of gas is directly proportional to the amount of gas present. This is known as Avogadro's law. It states equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. As small n is equal to capital N upon capital N naught, that is, number of moles is equal to number of molecules capital N divided by Avogadro's number, where capital N naught, Avogadro's number, is constant. Therefore, small n, that is number of moles, is directly proportional to capital N, that is number of molecules. Therefore, V is directly proportional to small n, that is number of moles. At constant pressure and temperature, volume is proportional to small n, which is known as Avogadro's law.
By combining the three laws, Boyle's law, Charles' law and Avogadro's law, we get an equation which gives the simultaneous effect of the changes of pressure and temperature on the volume of a gas. This is known as ideal gas equation. According to the Boyle's law, at constant temperature, volume of a given mass of gas is inversely proportional to applied pressure. This can be represented as shown on the screen. According to Charles' law, at constant pressure, volume of a given mass of gas is directly proportional to absolute temperature as shown on the screen. And according to Avogadro's law, equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. As number of moles, small n of gas are related to number of molecules n, we have small n is equal to n upon n0, where number of moles small n is equal to number of molecules n divided by Avogadro's number. N0 or Avogadro's number is a constant. Therefore, small n, that is number of moles, is directly proportional to n, the number of molecules, as shown on the screen. So, volume of gas is directly proportional to the amount, that is number of moles of gas at constant temperature and pressure. This is known as Avogadro's law. The three laws, Boyle's law, Charles' law and Avogadro's law, can be combined together in a single equation which is known as ideal gas equation. Combining Boyle's law, Charles' law and Avogadro's, we have volume is proportional to n multiplied by T upon P, which implies that volume is equal to a constant of proportionality R multiplied by n multiplied by T divided by P. Let me tell you that R is a constant of proportionality and is known as molar gas constant. On rearranging this equation, we obtain P multiplied by V is equal to n multiplied by R and T as shown on the screen. R is same for all gases, therefore it is also called as universal gas constant. This equation, P multiplied by V is equal to n multiplied by R and T, is called ideal gas equation. For 1 mole of gas, that is n is equal to 1, P multiplied by V is equal to R multiplied by T. Ideal gas equation is a relation between 4 variables and it describes the state of any gas. Therefore, it is also called as equation of state. The ideal gas equation is the relationship for the simultaneous variations of the variables. If temperature, volume and pressure of a fixed amount of gas vary from T1, V1 and P1 to T2, V2 and P2, then we can write P1 multiplied by V1 upon T1 is equal to n multiplied by R and P2 multiplied by V2 divided by T2 is equal to n multiplied by R, which implies that P1 multiplied by V1 upon T1 is equal to P2 multiplied by V2 upon T2, is a very useful equation. If out of 6 values of 5 variables are known, the value of unknown variable can be calculated from the equation. This equation is also known as combined gas law.
Let us now learn about nature of the universal gas constant R. Children, now we will find out dimensions of gas constant from ideal gas equation. We know that P multiplied by V is equal to n multiplied by R and T, which implies that R is equal to P multiplied by V upon n multiplied by T. Or we can say that R is equal to pressure multiplied by volume divided by moles multiplied by temperature. Since pressure is force acting per unit area, R will be equal to force divided by area multiplied by volume divided by moles multiplied by temperature. Since area is equal to length square and volume is equal to length cube, so that R is equal to force multiplied by length cube divided by length square whole divided by moles multiplied by temperature, which is equal to force multiplied by length divided by moles multiplied by temperature. But we know that force multiplied by length is equal to work. Therefore, R is equal to work divided by moles multiplied by temperature. Thus, R represents work done per degree per mole of gas. R can be expressed in different units depending upon units of work. Volume of 1 mole of an ideal gas under STP conditions 273.15 Kelvin and 1 bar pressure is 22.7 decimeter cube. Value of R for 1 mole of an ideal gas is equal to 1 bar multiplied by 22.7 decimeter cube divided by 1 mole multiplied by 273.15 Kelvin, which is equal to 0.083 bar decimeter cube per Kelvin per mole. When pressure is expressed in atmosphere and volume in liters, 1 mole of gas under STP conditions at 273 Kelvin and under 1 atmospheric pressure occupies volume 22.4 liters. R is equal to 1 atmosphere multiplied by 22.4 liters divided by 1 mole multiplied by 273.15 Kelvin, which is equal to 0.0821 liter atmosphere per Kelvin per mole. When pressure is expressed in 1,01,325 Newton per meter square and volume in meter cube for 1 mole of gas at 273 Kelvin temperature, value of R is equal to 8.314 Newton meter per Kelvin per mole, which is equal to 8.314 joules per Kelvin per mole. Let us now solve a problem. At 25 degrees Celsius and 760 millimeter of mercury pressure, a gas occupies 650 milliliter volume. What will be its pressure at a height where temperature is 10 degrees Celsius and volume of the gas is 680 milliliters? And now let us discuss about the solution. It is given that P1 is equal to 760 millimeter of mercury. V1 is equal to 650 milliliter. T1 is equal to 25 plus 273 is equal to 298 Kelvin. V2 is equal to 680 milliliter and T2 is equal to 10 plus 273 is equal to 283 Kelvin. According to the combined gas law, P1 multiplied by V1 divided by T1, which is equal to P2 multiplied by V2 divided by T2. This implies that P2 is equal to P1 multiplied by V1 multiplied by T2 divided by T1 divided by V2, or P2 is equal to 760 millimeter of mercury multiplied by 650 milliliter multiplied by 283 Kelvin divided by 680 milliliter multiplied by 298 Kelvin, which is equal to 689.90 millimeter of mercury.
Students, let us now discuss ideal gas equation in terms of density or relationship between density and molar mass of a gas. Ideal gas equation is P multiplied by V is equal to N multiplied by R and T is equation 1. It can be rearranged as shown on the screen. N upon V is equal to P upon R multiplied by T. As N is number of moles is equal to small m, that is mass of gas in grams, divided by capital M, the molar mass of gas. Replacing N by small m upon capital M in equation 2, we get small m upon capital M multiplied by V is equal to small p divided by R multiplied by T, as m divided by volume V is density. We can also write the equation 3 as small d, that is density, upon capital M is equal to P upon R multiplied by T. On rearranging this equation 4, that is density upon M is equal to small p upon R multiplied by T as shown on the screen, we get the relationship for calculating molar mass of a gas as shown on the screen. Capital M is equal to small d multiplied by R multiplied by T divided by P. Dalton's law of partial pressures. The law was formulated by John Dalton in 1801. It states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases, that is, the pressures which these gases would exert if they were enclosed separately in the same volume and under the same conditions of temperature. In a mixture of gases, the pressure exerted by the individual gas is called partial pressure. Let P1, P2 and P3 and so on be partial pressure of gases 1, 2, 3 respectively. Then total pressure P total mathematically can be written as P total equal to P1 plus P2 plus P3 and so on at constant temperature and volume. P total is equal to the sum of the partial pressure P1, P2, P3, etc. exerted by mixture of non-reacting gases are generally collected over water and therefore are moist. Pressure of dry gas can be calculated by subtracting vapor pressure of water from the total pressure of the moist gas, which contains water vapors also. Pressure of the dry gas is equal to total pressure minus aqueous tension. Pressure exerted by saturated water vapor is called aqueous tension. Aqueous tension of water is different at different temperatures.
Students, let us illustrate Dalton's law of partial pressure with this animation. Student, ਤੁਸੀਂ ਇਸ ਐਨੀਮੇਸ਼ਨ ਵਿੱਚ 3.5 ਲੀਟਰ ਦੀ ਕਪੈਸਿਟੀ ਵਾਲੇ ਵੈਸਲ ਦੇਖ ਰਹੇ ਹੋ। ਪਹਿਲੇ ਵੈਸਲ ਵਿੱਚ ਹਾਈਡਰੋਜਨ ਦੇ 0.6 ਮੋਲਸ ਨੂੰ 2.9 ਐਟਮੋਸਫੇਅਰ ਦੇ ਪ੍ਰੈਸ਼ਰ ਅਤੇ 20 ਡਿਗਰੀ ਸੈਂਟੀਗ੍ਰੇਡ ਦੇ ਟੈਂਪਰੇਚਰ ਉੱਤੇ ਰੱਖਿਆ ਗਿਆ ਹੈ। ਸੈਕੰਡ ਵੈਸਲ ਵਿੱਚ ਹੀਲੀਅਮ ਦੇ 1.5 ਮੋਲਸ ਨੂੰ 7.2 ਐਟਮੋਸਫੇਅਰ ਦੇ ਪ੍ਰੈਸ਼ਰ ਅਤੇ 20 ਡਿਗਰੀ ਸੈਂਟੀਗ੍ਰੇਡ ਦੇ ਟੈਂਪਰੇਚਰ ਉੱਤੇ ਰੱਖਿਆ ਗਿਆ ਹੈ। Now if we put both the gases, hydrogen and helium, in the third container at the same temperature, this means that in the vessel 3 there will be 0.6 moles of hydrogen and 1.5 moles of helium, which is equal to 2.10 moles of mixture of non-reacting gases. ਅਸੀਂ ਵੇਖਦੇ ਹਾਂ ਕਿ ਥਰਡ ਵੈਸਲ ਵਿੱਚ ਗੈਸਾਂ ਦਾ ਟੋਟਲ ਪ੍ਰੈਸ਼ਰ ਹਾਈਡਰੋਜਨ ਦੇ ਪਾਰਸ਼ਲ ਪ੍ਰੈਸ਼ਰ ਅਤੇ ਹੀਲੀਅਮ ਦੇ ਪਾਰਸ਼ਲ ਪ੍ਰੈਸ਼ਰ ਦੇ ਜੋੜ ਦੇ ਬਰਾਬਰ ਹੋਵੇਗਾ। ਟੋਟਲ ਪ੍ਰੈਸ਼ਰ ਇਜ਼ ਇਕੁਅਲ ਟੂ pressure of hydrogen plus pressure of helium, which is equal to 2.9 atmosphere plus 7.2 atmosphere, which is equal to 10.1 atmosphere. आओ हुन applications of Dalton's law बारे जानदे हां. Let us study about determination of pressure of a dry gas. Students, we will determine pressure of the dry oxygen gas collected over the water. Potassium chlorate, that is KClO3, decomposes to potassium chloride, that is KCl, and oxygen gas when heated. MnO2 is added to speed up the reaction. The oxygen gas produced in the reaction can be collected by bubbling it through water and collecting it in a graduated cylinder. As oxygen gas is generated, the gas bubbles rise to the top and displace water from the cylinder. इस तरह collected oxygen gas pure नहीं हुंदी, क्योंकि cylinder ਵਿੱਚ ਇਸ ਨਾਲ water vapor भी present ਹੁੰਦੇ ਹਨ. The total gas pressure is equal to the sum of the pressures exerted by the oxygen gas and the water vapor. The partial pressure of dry oxygen equals to the total pressure minus the pressure due to water vapor. Children, let us now discuss partial pressure of gas in terms of mole fraction. Suppose at the temperature T, three gases 1, 2, 3 which do not react chemically are enclosed in a container of volume V. Exert partial pressure P1, P2 and P3 respectively. N1, N2 and N3 be their number of moles of these gases respectively according to ideal gas equation. Partial pressure of gas 1 is given by P1 is equal to N1 multiplied by R multiplied by T divided by V. Partial pressure of gas 2 is given by P2 is equal to N2 multiplied by R multiplied by T divided by V. Partial pressure of gas 3 is given by P3 is equal to N3 multiplied by R multiplied by T divided by V. Thus, total pressure is equal to sum of partial pressure of three non-reacting gases. That is, total pressure is equal to P1 plus P2 plus P3. By substituting the values of P1, P2 and P3 in this equation, we get which is equal to N1 multiplied by R multiplied by T upon V plus N2 multiplied by R multiplied by T upon V plus N3 multiplied by R multiplied by T upon V, which is equal to N1 plus N2 plus N3 multiplied by R and T divided by V. On dividing P1 by P total is equal to N1 divided by N1 plus N2 plus N3 multiplied by R multiplied by T multiplied by V divided by R multiplied by T and multiplied by V, which is equal to N1 divided by N1 plus N2 plus N3, which is equal to N1 divided by N, as N equals to N1 plus N2 plus N3. N is total number of moles. N1 divided by N is equal to chi1. Chi1 is called mole fraction of first gas. Thus, partial pressure of first gas P1 is equal to mole fraction of first gas chi1 multiplied by P total. P1 is equal to chi1 P total. Similarly, for other two gases, we can write partial pressure of second gas P2 is equal to mole fraction of second gas chi2 multiplied by P total, and partial pressure of third gas P3 is equal to mole fraction of third gas chi3 multiplied by P total. Thus, a general equation can be written as Pi is equal to chi P total, where Pi and chi are partial pressure and mole fraction of ith gas respectively. If total pressure of a mixture of gases is known, the equation can be used to find out pressure exerted by individual gases. Children, let us have a look at one more problem. A neon dioxygen mixture contains 70.6 grams dioxygen and 167.5 gram neon. If pressure of the mixture of gases in the cylinder is 25 bar, what is the partial pressure of dioxygen and neon in the mixture? And now the solution. Number of moles of dioxygen is equal to 70.06 gram divided by 32 grams per mole, which is equal to 2.21 mole. Number of moles of neon is equal to 167.5 grams divided by 20 grams per mole, which is equal to 8.375 moles. Mole fraction of dioxygen is equal to 2.21 divided by 2.21 plus 8.375, which is equal to 2.21 divided by 10.585, which is equal to 0.21. Mole fraction of neon is equal to 8.375 divided by 2.21 plus 8.375, which is equal to 8.375 divided by 10.585, which is equal to 0.79. Alternatively, mole fraction of neon is equal to 1 minus 0.21, which is equal to 0.79. Partial pressure of a gas is equal to mole fraction multiplied by total pressure, which implies that partial pressure of oxygen is equal to 0.21 multiplied by 25 bar, which is equal to 5.25 bar. And partial pressure of neon is equal to 0.79 into 25 bar, which is equal to 19.75 bar.
ਬੱਚਿਓ, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। Thanks for your attention and see you in the next class. Goodbye.